So, what we have seen is that the motion of the fluid or the flow of the melt in a steel making reactor such as ladle, tundish, mold or a converter is the consequence of various kinds of forces, and consideration of these forces give us the necessary framework to develop the dynamic similarity criteria. And I have indicated that in systems where inertial forces, gravitational forces, viscous forces and pressure forces are only relevant, there the similarity can be expressed in terms of two limiting consequences, that is the Reynolds number in the model is equal to Reynolds number in the full scale, and Froude number in the model is equal to Froude number in the full scale. So, if you can maintain these, additional numbers are going to follow if we have more number of forces that I have already discussed. So, if you can maintain these two equality, in that case we can say that yes, the systems are dynamically similar. Of course, before we can do this, we have to respect the geometrical similarity. So, geometrical similarity plus satisfying Reynolds similarity as well as the Froude similarity will ensure that the two systems are going to be dynamically similar. Now, let us look at the definition of Reynolds number. Reynolds number, as we know, is the viscous force by inertial force by viscous force. Now, inertial force as an expression like LC square and viscous force as an expression like UC into LC. So, this is a dimension of Newton, this will also have a dimension of Newton, and if we simplify this, then we get rho UC LC. This is a traditional definition of Reynolds number as we encounter. These two are the respectively density and viscosity of the melt. UC is the characteristic velocity, LC is the characteristic length. Now, what is the characteristic length and characteristic velocity and the characteristic length scale? These are the velocity and length scale of the system that are relevant for the present analysis. So, I am going to explain that a bit more when I write down. Similarly, we can say that the Froude number definition accordingly will come out to be so we can write down inertial force, in the denominator we have gravitational force. So, rho times g times volume and L square actually how it comes, let me say it comes out like this is the same expression of inertial forces and gravitational forces is rho g into L cube LC cube. So, we have rho cancels out, LC square and LC square cancels out. So, we have LC L sub c in the denominator, and that is how. So, this is the inertial force and this is the gravitational force, and the definition of Froude number is the characteristic velocity square divided by acceleration due to gravity in the length scale. Now, the characteristic velocity, coming back to the issue of characteristic velocity and the characteristic length scale, these are the velocities and the length scales which are known to us. Now, for example, I have a gas stirred ladle system, I can say, where I have a porous plug located at the bottom, say. You can say I have depth of liquid L and I have a radius or a diameter of the vessel, okay. And if it is, whether L, this depth of the liquid should represent the characteristic length, or the radius of the vessel or the diameter of the vessel should represent the characteristic length, that is an important issue to decide, because it is not usually forthcoming. For example, in tundish you may have three different length scale: length of the tundish, width of the tundish, okay, and depth of liquid in the tundish, and of this which one has to consider in order to. So, as you have seen that the forces acting in the system, so this is the inertial forces which is acting on the system, and the inertial forces is as a result of the fluid motion, and we have to understand that which corresponds or which is a more meaningful entity, either the length scale or the radius of the vessel, which should come into the consideration of characteristic length. Similarly, a characteristic velocity. What is that velocity? Is it this velocity through the orifice which should come into this particular expression, or it is some other scales of velocity? So, it is some amount of thinking about the process is necessary before one can explicitly quantify that what is the characteristic length and what is the characteristic velocity scale, because there are multiple number of characteristic length scale and characteristic velocity, or length scale and velocity scale, which are there in the system, and of these only one you can take or consider as a characteristic length scale and characteristic velocity scale, which can be used here to determine the relative magnitude of the two dimensionless groups. Now, one point you can note here that the Reynolds number depends on thermophysical properties of the fluid. Density comes into the picture, viscosity comes into the picture. On the other hand, Froude number does not depend on the thermophysical properties of the liquid. Okay, it is independent. So, therefore, if I can say somehow that a phenomena is Reynolds dominated, one of the limiting conditions that if you can approximate the system as a Reynolds dominated system, and Reynolds dominated system means the Reynolds number is not very large. Okay. So, therefore, we can say that the viscous force is very small, and in that case viscous force is very large, and in that case the Reynolds number is actually very small. So, we can say it is a viscous force dominated situation, that essentially is Reynolds number governed flow. On the other hand, if you say that it is inertial and gravitational force dominated system, in that case I can say that it is a Froude dominated system. So, I repeat again. So, if I say that we have inertial force and viscous forces are important, but gravitational forces are not important, then I can characterize the system to be Reynolds dominated. On the other hand, if I say that the system is governed by or dominated by inertial forces and the gravitational forces and viscous forces is not important, in that case I can say it is a Froude dominated system. So, therefore, if the system is Froude dominated, if this number governs the process, in that case we must understand whatever is the fluid that we use has no consequences as far as dynamic similarity criteria is considered. Okay. So, therefore, we will come back to this issue in a minute, but now let us say that what is the fluid that we want to use here, and then this issue of Reynolds dominated flow versus the Froude dominated flow will be more clear to us. But in essence, for accurate modeling, we would like to respect both Reynolds equality and Froude equality in those situations where the inertial, viscous, gravitational and pressure forces are important. But we may see that it may not be always possible to maintain both these equalities simultaneously, as is going to be evident from our analysis. Now, suppose the full scale system which contains molten steel is this, and this is the model system, and this is the full scale system, and we have similarly we have a porous plug here, and through the porous plug we have argon injection, and this is liquid steel, and this is, suppose for the time being I say that I use a fluid which is water. So, I want to make a transparent model because I want to visualize the flow. Now, I can, of course, as you will see later on, I can mathematically model the flow in the system and find out that what is the velocity here, what is the velocity here, what is the velocity here. I can map the velocity. This is called scientific visualization. Okay? And on the other hand, if I create water, I can physically see how the flow is going on, provided the vessel is made out of some transparent material like perspex or glass. So, this is called a physical visualization. So, when I construct a physical visual model, I am considering or I am examining the possibility of physical visualization of the flow, and therefore, I can find out that, well, if I use water, then in that case I can visualize the flow very nicely if the entire ladle is fabricated out of plexiglass or transparent plastic sheets. On the other hand, I would say, if you say, sir, I want to use mercury, in that case I would say that physical visualization of the flow is not possible because mercury is not transparent. So, using water gives us many advantages. one of the advantages, or the first very advantage is water is a cheap liquid. The second advantage is that it is non-corrosive, it is non-hazardous liquid, and the third, from the viewpoint of studying the process, it is extremely important to recognize that water is transparent. So, therefore, we can very conveniently physically observe the flow pattern. For example, if the flow is there and I add a drop of potassium permanganate, then I can see how does the color distributes, and thereby I can very clearly see that what is the flow pattern in the system because of this kind of a gas injection through a porous plug. So, physical visualization is possible with water, and that is why water as a replacement for liquid steel is has been very popular. And as I have mentioned already, using water as the bulk fluid makes this process what we call as a, or known as a, aqueous modeling or water modeling. So, for the time being, let us assume that we in our laboratory, for the sake of convenience, we would like to use water. Now, one important point which all of you must note, that water at room temperature, if you are using at 25 degrees centigrade, steel at 1600 degrees centigrade, their kinematic viscosity is approximately equal. I think, why should I say approximately? It is, I think, within 1% actually the value. It is, I can, for as a first approximation, I can say that is almost equal to nu water. So, but note that these are state properties. So, therefore, I must mention that they are at the room temperature. So, this is 25 degrees centigrade and this is 1600 degrees centigrade. And what is the value? The value is in SI unit, it is approximately 10 raised to the power minus 6 meter square per second. This is the value. So, now if we use water, now I have constructed a water model, I have chosen a scale factor. Suppose I say that lambda is equal to 0.3. This is what I have chosen. Now, I find out, I have to mention, now I have to consider these two equalities in order to. So, I have geometrically made the vessel similar to a full scale system. I have scaled it down in size in terms of the chosen scale factor. For the sake of convenience, I have used water, and now I want to find out that the systems have to be dynamically similar. So, this equality and this equality has to be respected. Now, you must remember, when I know the argon gas flow rate in the full scale, the flow rate of air here, if you are using as a replacement, is really not known to us. Everything else, I have scaled it down, I have used water, everything is set except for one single parameter, that what is this argon flow rate or air flow rate that we are going to use through this, while this flow rate in the full scale is known to us. This is not known to us, and this will be known by considering these two equalities and the necessary flow rate which will have to be injected in the model and which will generate a flow pattern in the system that will make this system dynamically similar with the full scale system. So, therefore, by consideration of the dynamic similarity criteria, the flow rate is going to be derived. So, let us see, let us try to make now the Reynolds number in the model equal to Reynolds number in the full scale. So, we say, as you see, that what is kinematic viscosity? The kinematic viscosity is actually dynamic viscosity divided by density. That is the definition of kinematic viscosity. So, I can say that Reynolds model criteria 1 and criteria 2. So, criteria 1 would give us U characteristic model by U characteristic full scale is equal to L characteristic model, nu characteristic or nu model, and L full scale into nu full scale. But by definition, L characteristic ratio of the characteristic length is equal to lambda. So, I will write down that this is equal to lambda raised to the power minus 1, because it is characteristic length of the model divided by characteristic length of the full scale is equal to lambda. So, the lambda is in the denominator, and then because nu model is equal to nu full scale, I have already said that I am using water in place of steel, their kinematic viscosity being identical. So, I can say that this term and this term will cancel out, they are approximately equal, okay, and therefore, the characteristic velocity scale in the system are inversely proportional to the geometric scale factor. This is the consequence of Reynolds equality. Let us look at the Froude equality, and the Froude equality will tell us that, well, UC model by UC full scale is equal to, then we take LC model by LC full scale, characteristic length full scale, raised to the power half. Because it is UC square, so the ratio of the velocities are going to be square root of the ratio of the characteristic length. The acceleration due to gravity will vanish from both the sides, and this tells us lambda to the power half. Now, one criteria says that the ratio of the characteristic velocity scale is inversely proportional to the Reynolds similarity demands that the ratio of the characteristic velocity scale should be inversely proportional to lambda. The Froude equality criteria demands that the characteristic ratio of the characteristic velocities in the two systems to be proportional to lambda raised to the power 5, lambda raised to the power half. So, these two criteria, the Reynolds criteria and the Froude criteria, therefore, cannot be respected simultaneously. We cannot meet them. You see, they are the one and the same equation, but giving us a different functional relationship. So, therefore, we will not be able to maintain these two equalities simultaneously when we use kinematic viscosity of the model. We use a fluid whose kinematic viscosity is identical to the kinematic viscosity of the full scale system. So, we make a very important deduction at this particular stage. In reduced scale modeling, okay, going back to this equation, both these conditions, both this equation can be respected only for one single value of lambda, and that lambda is going to be equal to unity. So, in full scale system, if the size of the model vessel is exactly equal to the size of the full scale system, in that case we can say that I can respect both this Reynolds and the Froude similarity simultaneously, even though I may be using a fluid which has the same kinematic viscosity as that of a steel. Alternatively, if I say that no, I am talking of a reduced scale modeling, in that case I will make this particular assumption, this particular assertion, that in reduced scale modeling, employing a fluid having the same kinematic viscosity as that of the full scale system, it is impossible to regard both Reynolds and Froude similarity simultaneously. So, then what is the way out? So, we have to make now one assumption, and this is the limiting assumption. We have to say, and I come back to that point which I have just now mentioned, that of all the forces which are acting in the system, are all the forces equally relevant? If they are equally relevant, in that case we cannot make any simplification. My objective now is to analyze the process and throw out one of these two criteria entirely from the analysis, but I have to rationalize this. Now, these are the consequences of inertial, viscous and gravitational forces. In steel making systems, we note that the size of the reactor is very, very large. So, LC is going to be, the characteristic length is large. Similarly, the level of agitation in steel making system is also going to be very, very large. Okay? So, the velocity is also very, very large. This is also expected to be large in steel making system, and the kinematic viscosity is going to be extremely small. So, therefore, I can look at these parameters mu by, if I now consider this as this, one and the same thing. So, I have removed density and viscosity and replaced viscosity by the kinematic viscosity, which is viscosity divided by density. Okay. So, now if we look at this order of these values, what could be the value of LC? Maybe of the order of 1 meter. That means the reactors are 3 meter in size, 4 meter in size. They are not 1 centimeter or 5 centimeter in size. Characteristic velocity is very, very large. It depends on what you are talking about. If you are talking about a furnace tapping operation, in that case the extent of stirring in the ladle can be of the order of tens of meters per second. On the other hand, if you are talking about gas stirred ladle system, inert gas injection, in that case the order of the velocity could be 1 meter per second. So, as a first approximation, let us say that we are talking of 1 meter per second, and then the kinematic viscosity is small and the value is already given. So, therefore, we find that the value of the Reynolds number will come out to be, on the basis of this order of magnitude analysis, of the order of 10 raised to the power plus 6. What does this number indicate? This number indicates that the inertia force in the system is 1,000,000 times larger than the viscous force. Similarly, if we analyze the ratio of this number, okay, which comes out to be Froude number, which is equal to uc square by acceleration due to gravity. So, this is 1, okay, uc is of the order of 1, this is LC, characteristic length is of the order of 1. So, this Froude number will come out to be of the order of 10 raised to the power minus 1, sorry 10, because acceleration 10 raised to the power minus 1, because g is approximately 9.81, which I am taking it to be equal to 10. So, it is this order of this magnitude will come out to be 10 raised to the power minus 1, which will essentially tell us that the gravitational force is 10 times larger than the inertial force itself. So, therefore, Reynolds number tells us that inertial force is much larger than the viscous force. The Froude number order of magnitude value tells us that gravitational force is larger than the inertial force. So, therefore, I can say that, well, the viscous force in gravitational force is larger than the inertial force, and the inertial force is much larger than the viscous force, which tells us that of the various forces which are acting in the system, the viscous forces are least. They have no consequences as far as the flow of the fluid in the system is concerned. So, therefore, we can say that, well, let us forget about the viscous force. The similarity of viscous force is not an issue as far as deriving the dynamic similarity criteria is concerned. So, if we throw out the viscous force, in that case, what are the forces we are remained with now? We have here, for example, as I said, I started the discussion by assuming pressure force, viscous force, and then we have inertial force, and we have gravitational force. And based on that, I have derived this criteria, and I have also shown that when these are the 4 forces, then I can say that, well, in non-dimensional form, this functional relationship holds good. But now, if I say that, well, the pressure force is there, the viscous force is not there, inertial force is there, gravitational force is there, only 3 forces are there, in that case, the functional relationship will boil down to, I have thrown out by doing this analysis Reynolds number. And why I have thrown out? Because I want to use reduced scale modeling in my laboratory. I want to use water, and I cannot respect both Reynolds and the Froude similarity simultaneously. So, as a result, I have to disregard one of these 2 numbers, and now I am doing an in-depth analysis of the process and trying to assign some order of magnitudes, and thereby I come to this conclusion that the viscous force in the system is perhaps not so important, and therefore we can ignore it, and therefore the forces which are relevant in the system are actually this, under the assumption, while we have started the analysis with this, and this was the non-dimensional representation. Now, if pressure force, inertial force, and gravitational force are there, are the relevant forces in that case, this is the limiting expression, and therefore I can say that, well, now I am going to remove this, that Reynolds criteria in reduced scale modeling using water is not so important, and hence we can consider that dynamic similarity of steel making system are going to be defined only by this single criteria, provided surface tension and other forces are not relevant itself. So, therefore, we will make this assertion that steel making systems are Froude number dominated systems. They are the systems which are dominated by inertial as well as gravitational forces. So, the consequence of stating that the Froude number equality holds good, or this represents the modeling criteria or dynamic similarity criteria in reduced scale modeling using water, we can say that therefore, the characteristic velocity scale in the system are going to be related in proportion to lambda. So, the characteristic velocity in the two systems are going to be related in terms of the scale factor in accordance with this equation, provided we say that the system is dominated by Froude number. So, we will have geometrical, I will tell you now that on the basis of this, how the argon flow rate can be calculated or known from the full scale once the full scale flow rate is given to us. But before we do that, I am going to also say a few words about kinematic similarity. So, dynamic similarity between model and full scale is going to be maintained when the systems are Froude dominated with this particular criteria. So, geometrical and dynamic similarities are criteria can be derived very easily or known to us on the basis of the analysis that I have just now presented. Now, kinematic similarity. So, this is the similarity of forces, and kinematic similarity talks about similarity of velocity. Similarity of velocity, and this is kinematic. It is defined like corresponding particles in model and full scale describe the same type of path or straight lines in corresponding intervals of time. So, the consequence, if the systems are kinematically similar, then you can see that, well, if this is my full scale ladle, and suppose in the full scale ladle the flow is going something like this, and if it is my model ladle, and in the model ladle also you will see that the similarity of flow pattern is an essential reflection of kinematic similarity. Kinematically similar are those systems which exhibit a similarity in flow fields, and we define it like this, that corresponding particles in model and full scale system trace out similar, geometrically similar paths in corresponding intervals of time. Now, if I say, therefore, let us look at the consequences. We know that LC model, characteristic length in the model and characteristic length in the full scale, is going to be always equal to lambda. And kinematic similarity says that we are going to have a characteristic, suppose time scale TC, characteristic time in the model by characteristic time in the full scale, and that is equal to some constant C sub t. I do not know that constant value of the constant, okay, but we must understand that on the basis of this I can find out that what is the corresponding ratio of velocity. The consequence of this is going to be, for example, V characteristics, I can say, therefore, on the basis of this model by U characteristic full scale is going to be equal to U characteristic model is nothing but L characteristic model by T characteristic model, and this is going to be L characteristic full scale divided by T characteristic full scale. Length by time is nothing but velocity. So, once these proportionalities are maintained, I should be able to find out that what is the corresponding ratio, and therefore, I can say that this is going to be equal to L characteristic model by L characteristic full scale into T characteristic full scale by T characteristic model, and this I have seen to be equal to lambda, and this is equal to C sub t inverse. So, this is equal to C sub t inverse. I can say that, well, if the system is now Froude dominated, for example, then I already know what is this particular ratio, right. What is this particular ratio? This is equal to lambda to the power half, provided the system is Froude dominated, because I have shown you that the characteristic velocity scales are in proportion to lambda raised to the power 5. So, therefore, I should be able to say that what is the corresponding, and this comes out to be therefore Ct is equal to lambda. I take it to the other side. So, this becomes C sub t lambda divided by lambda to the power half is equal to lambda to the power half. So, the corresponding time scales in the system now is known in terms of the scale factor lambda itself. So, the concept of that, as I mentioned, that corresponding particles in model and full scale systems trace out geometrically similar paths in corresponding interval of time, and that corresponding interval of time will be governed by this particular relationship, which gives us that the time scale in the model and the full scale system, the ratio of the time scales in the model and the full scale system is equivalent to lambda raised to the power half. So, therefore, in one case, in the full scale case, if it is, for example, Ct is equal to, I can say roughly lambda, suppose if I take lambda is equal to 0.3, in that case, say lambda to the power half is going to be is equal to roughly about say 0.5. Okay, approximately I am saying this is going to be 2.5, maybe 5.7 or something like this. Okay. So, therefore, if I know that, therefore, this value is going to be is equal to C sub t. So, if I put this 0.57 here, I will be immediately able to know that if I am talking about 1 second time in the full scale system, that 1 second time actually corresponds to 0.57 seconds time in the model system. If I am talking about 10 seconds time in the full scale system, I will be talking about 5.7 seconds in the model system, and in this way I should have an idea of the correspondence between the time scales in the two system itself. So, let us consider now the dynamic similarity and show you that how can you really model the argon flow rates based on the consideration, because one issue needs to be now sorted out that, well, we have considered the flow pattern. Of course, now is not like this. The flow pattern will go something like, it goes something like this, and then it goes something like this. It is displaced towards the, it goes something like this. So, you have rising velocity here because the gas is rising up, and then the gas lifts surface, and that is how the surrounding goes. And the systems, suppose they are dynamically and kinematically similar. So, that is why I have. But as I mentioned to you, while these dimensions are known to me, these dimensions are known to me. This is the central line, this is the central line, and note that I am always drawing the porous plug displaced from the central line, because you remember that I said that this is to be converted later on to a ladle furnace, and in ladle furnace we do not want the porous plug to be located immediately below the electrodes, because it is going to otherwise lead to electrode hunting or electrode consumption. Okay, that is why this porous plug is always displaced towards the wall. Now, this dimension L, this is the depth of liquid. I am not saying this is L sub C, this is L and this is R. So, this is R sub full scale, this is L sub full scale, this is L sub model, and this is R sub full scale, R sub model. So, these dimensions I have obtained once I have selected that, well, lambda is equal to 0.5. The nozzle diameters are not so important to us. You again remember I said that in the context of gas stirring in ladles, that conditions at the nozzles or the orifice are not critical to the flow recirculation, because these are the systems which are driven by potential energy rather than the kinetic energy of the injected gas. The kinetic energy of the injected gas depends on the nozzle diameter, but the potential energy or the buoyancy energy which is supplied by the rising bubbles does not have anything to do with the porous plug or the nozzle. It depends on the equilibrium size of the bubbles or the distribution of bubbles in the system itself, which is governed by thermophysical properties of the fluid. So, therefore, whether the injection of gas in the model in the full scale system is by porous plug or I use a nozzle here or an orifice here, it has hardly any consequence. What matters here is that what is the flow rate of air or argon, which I say Q air, for example. Q is the volumetric flow rate, is the usual representation, and I say that this is not known. On the other hand, Q argon is known. So, having similarity for the nozzle does not make any difference. We can use anything what we want to have. We only want to find out that what is the flow rate. So, this case therefore becomes somewhat distorted model, because I am not scaling the nozzle dimensions, okay, but as I mentioned that my understanding is like this, as I have mentioned to you also that hydrodynamic conditions at the orifice or nozzle is not critical to flow recirculation. So, therefore, I need not try to scale down these dimensions, I can disregard this. So, to someone else it may look like a distorted model, but to people who understands the little hydrodynamics well, they can say no, even this model with not a porous plug, but some kind of a tuer, give us the right kind of a simulation or right kind of a correct dynamic similarity, provided we can appropriately scale the flow rate which is needed here. Okay. So, let us make few idealizations as we go on to derive that what is an appropriate volumetric flow rate needed in the model in order to have this dynamically similar with this, because I told you that metallurgical systems or steel making systems in particular are extremely complex. So, therefore, we have to make certain assumptions and certain idealizations, and even then we may see sometimes that the analysis does not produce much convincing result. So, let us for the time being demonstrate to you by considering a central gas stirred ladle system. By central gas stirred ladle system, I mean that well, I have a porous plug or a nozzle which is located at the central line. The theories are well understood about central gas injection, even though the central gas injection is not practiced in the industry. So, we have something like this, a two phase plume which develops here. I am drawing an idealized plume boundary, and that is how. So, the gas is injected from the bottom, and once gas is injected, it creates bubbles here, the bubbles rise, and as a result of which the fluid moves in this particular fashion. So, I can say that well, this represents my vessel. Now, in this system, as per our earlier assumption that we are considering, Froude number is the only relevant dimensionless number which governs the modeling or the dynamic similarity criteria, and let us assume that the system is geometrically similar, and now our objective is to find out that what is that flow rate. So, therefore, in this system we have inertial force and viscous forces, which are inertial force and gravitational forces which are important, okay. And the modeling criteria is solely expressed in terms of Froude number in the model must be equal to I am going to show that by considering this similarity number, the similarity of the Froude number or equivalence of Froude number between the model and the full scale, an expression for model flow rate of gas can be found out in terms of the full scale gas flow rate. Let us now put what is the definition of Froude number. We have it is inertial force by gravitational force, that is equal to Froude number. Now, let us, this gravitational force here essentially is the buoyancy force, okay, or we can say that the net force, net gravitational force is the buoyancy minus I am going to explain this to you. So, this is the net buoyancy force. Okay, there is a density difference, rho liquid and rho gas. So, one is the weight of the bubble, another is the related with the weight of the liquid, okay, which is the equivalent to the displaced volume or the mass of the displaced fluid. Now, this represents the buoyancy force per unit volume, buoyancy force per unit volume. In this system, where are the buoyancy forces acting? The buoyancy forces are acting only within the two-phase flume region. There is no buoyancy force here, there is no buoyancy force here. Okay? So, I am going to find out now a ratio of the inertial to gravitational forces or buoyancy forces within the plume region itself. And if I say that let me now idealize this plume in terms of an equivalent cylinder. What do I mean by an equivalent cylinder? I mean by an equivalent cylinder is that the volume of the cylinder is exactly equal to the volume of the idealized two-phase cone, which is the gas liquid conical region that I have drawn here. So, the cylinder has, and this therefore represents the volume of the cone, conical plume, volume of conical plume, which is equivalent to volume of equivalent volume cylinder, which I have equivalent volume cylinder. And R sub I therefore represents, this E represents the equivalent volume, it is the radius of the equivalent volume. So, this essentially represents what is my R sub E, the radius of the equivalent volume cylinder. So, buoyancy force per unit volume multiplied by the volume of the two-phase region gives us the gravitational force or the buoyancy force which is acting, this I can say buoyancy force or gravitational force. This is associated with the acceleration due to gravity, and this is the total buoyancy force which is acting, gravitational force which is acting within the two-phase flume region. And now, considering that the gas density is very, very small, I can say that I can also write that this is what is alpha average means? The alpha average means that we have some gas volume fraction here. So, maybe 10%, 20% or 5% of the gas volume gases are occupied. So, the plume has a volume. So, this alpha average multiplied by the total volume pi R square L represents what? This represents the volume of gas which is present in the two-phase region. In reality, as I have mentioned earlier in the context of secondary steel making, discussion on secondary steel making or ladle metallurgy, that there is going to be variation of gas volume fraction, but as I said, we are finding out a modeling criteria based on some sort of idealizations and assumptions. So, for that sake, we have assumed that let the volume fraction of gases be distributed eventually, there is an uniform average gas volume fraction which is nothing but alpha average. Even though we may have variation in gas volume fractions, we can integrate that over the plume and find out an average or a representative gas volume fraction. So, this represents the total amount of gas which is present in the two-phase plume region. This is the expression of buoyancy force. Now, let us look at the inertial force within this. So, visualize this to be like you have a cylindrical region and you have a two-phase mixture which is flowing. It is like a, you can visualize this cylinder like a pipe and then the flow of fluid through a pipe. Only thing is that we are having flow of a gas liquid mixture. So, by definition, again the inertial forces, as we have seen, it is rho mixture because that is the density of the fluid. You remember what I have written for inertial force expression. The inertial force expression is nothing but density multiplied by the velocity square multiplied by the cross sectional area. So, inertial forces acting within the two-phase region is equal to u sub p square, and I am assuming that the gas liquid mixture is rising with a constant velocity which is normally called the plume rise velocity, and this also I have discussed in the context of secondary steel making or ladle metallurgy. So, the plume rise velocity essentially is the upward rise velocity of the gas and the liquid mixture. So, if that is the velocity and it is constant across the length, again this is an idealization, and then I can say that pi r e square is the cross sectional area. So, therefore, this now represents the inertial force. So, I have got an inertial force which is acting in the plume region. I have got the buoyancy force which is acting in the plume region. Now, if I take the ratio of the two, then I can find out, let me just quickly erase this and then show it to you, that inertial force by gravitational force, which is the definition of Froude number. So, therefore, the Froude number will come out to be rho mixture up square into pi r e square, and here we are going to have rho liquid alpha average into pi r e square. So, I can say that now, coming back to this, if you remember, I also mentioned that gas volume fraction within the plumes are going to be very, very small, because the injection flow rate in little metallurgy steel making is small. So, therefore, we can say that the density of the liquid, what is the mixture density? The mixture density actually, as per the continuum approach, is rho liquid into alpha liquid plus 1 minus alpha L, or which is equal to into rho g. So, alpha g, this is equal to actually 1 minus alpha L. Alpha L is the volume fraction of liquid, alpha g is the volume fraction of gas. Alpha g plus alpha L is equal to 1, because in any control volume, for example, here alpha L is equal to 1, alpha g is equal to 0. Here we have finite value of alpha g, we have finite value of alpha L. So, the weighted average of the gas density, liquid density plus the gas density is equal to the mixture density. Just like the way you say, if you have a matrix of different materials, for example, you have perlite which consists of ferrite and cementite. So, how do you say the hardness of perlite? So, you say volume fraction of ferrite multiplied by hardness of ferrite plus volume fraction of cementite plus into hardness of cementite, and then you find out which is called a volume fraction or weighted average hardness, or hardness based on volume fractions. So, it is based on the continuum approach, and this is the way, the same way you define the hardness for a composite material. You can say that the mixture density is going to be the fraction of the liquid density plus a fraction of the gas density, and that is what it is. Now, if the gas volume fraction is very, very small, in that case we can say that, well, I can approximately consider that rho liquid is approximately is equal to rho g, and this is going to be true provided the gas volume fraction is very, very small. And as I have shown in the context of little metallurgy, that 2 to 5% of gases are there in the plume region, which makes us this kind of a which tells us that this kind of a simplification is indeed possible. So, if that is so, then I can say, we can say that this equation will boil down to G into alpha average into L. So, now this is the definition of the Froude number, and therefore, I can say, I come back here and show you, therefore, from the equation that Froude model must be is equal to Froude prototype or full scale, I can say that up square G alpha average into L in model is equal to up square G alpha average. I make one drastic assumption, but not too unrealistic. If the plume angles are not too different and the flow rates are small, I would expect that, well, if the gas volume fraction in model is 2 to 5%, similar kinds of a gas volume fraction will also be there in the full scale system, because we are talking of the similar flow rate ranges in between the model as well as in the prototype. So, as a first approximation, I can say that, well, alpha average in the model is equal to alpha average in the full scale. If I make that assumption, in that case it turns out that now UP model by UP full scale will come out to be lambda raised to the power half. So, I can erase this now, there is no necessity of, so I can say L. And so, once I do this, one important thing comes out here, that although the system has both radius as well as the depth of the liquid, my analysis tells that the characteristic velocity in the system is the plume rise velocity. It is not the velocity through the orifice. That has nothing to do with the system. Similarly, this analysis tells us that the characteristic length, you remember the Froude number was characteristic length divided by characteristic length square divided by G into characteristic length, and therefore, in place of LC, what has come here? L has come, which is this depth. In this analysis, we do not see radius of the vessel coming into the picture. So, therefore, we conclude that the analysis tells us that in the system, okay, the depth of the liquid is a more representative length, because you remember the potential energy supplied by the gas depends on the depth of the liquid. Okay, larger is the depth of the liquid, more is going to be the liquid recirculation in the system. So, it is this particular direction which is important in quantifying the forces which will be acting over the liquid, and not this particular dimension. So, therefore, the analysis shows that indeed the depth of the liquid is a meaningful length scale as far as ascribing one of the two characteristic length parameters to a characteristic length itself. So, therefore, we conclude that in the case of ladle systems, gas stirred ladle systems, we can consider the plume rise velocity to be a characteristic velocity and the length scale, the depth of the liquid as a characteristic length scale. Now, we have an expression for plume rise velocity, as I have shown you that what is the plume rise velocity in SI unit. This comes out to be something like 3.5, that is 3.3 into q raised to the power minus 1 by 3 plus 1 by 3, L raised to the power plus 1 by 4 and R raised to the power minus 7 by 12. The plume velocity increases as I have given some other expression when I was talking, because there are many expressions which are available in the literature, and these expressions are more or less similar and produce equivalent results. So, in SI unit meters per second, this is the gas flow rate raised to the power 1 by 3, which tells us increase the gas velocity, plume rise velocity increases. Same is true with L, but it obeys an inverse relationship with R, which tells us that larger is the radius of the vessel. Now, we also note that L model by L full scale is equal to R model by R full scale is equal to lambda. This relationship always holds good because the systems are geometrically similar. So, if I now substitute this equation into this particular expression, in that case I will be able to replace L and R in terms of lambda, and the entire equation will boil down to an expression relating Q in model to Q in full scale in terms of lambda, because R, L and R can be replaced in terms of lambda. And if you do that, we will find out that Q model, this equation and this expression. So, use this expression using A, I can say. So, I can say if you use A, then you can say Q model by Q full scale will come out to be. So, therefore, the flow rate scaling equation boils down to Q model is equal to Q full scale raised to the power lambda by 5. So, therefore, this is the final expression, and I would say that if you know now the scale factor, and since you know the full scale flow rate, you should be able to find out that what is the model flow rate. So, having found out the model flow rate, that you have geometrical similarity already, that nozzle or tuer or porous plug is irrelevant, no issue of settling similarity at this particular point. We can say by using this flow rate in accordance with the equation here, I can find out. So, for example, I can say that if you know this lambda to the power 5 by 2 comes out to be 0.1, and if you are using a model flow rate which is 100 meter cube per second, in that case 100 multiplied by 0.1. So, 10 meter cube per second of flow rate you have to use here in order to get. So, corresponding to the full scale flow rate and the chosen scale factor, you are going to have model flow rate, and therefore, with that model flow rate you will ensure dynamic similarity between the two. So, once the flow rate, right flow rate is used, and this flow rate, therefore, I am going to say it is going to be Q full scale. What is the flow rate that you are going to using? Into lambda to the power 5 by 2, and that is the flow rate actually you are going to introduce into, and this flow rate if you use, then I am going to say that this system is going to be dynamically similar with the full scale.